All right, we can get started. I'm Radha Nagarajan from Marvell. I'm going to talk about 2.5D heterogeneous integration for silicon photonics optical engines. If you have been part of the whole track from the beginning, I won't need an introduction to what we are trying to do, but you heard a talk from Intel and Broadcom earlier on before the break. So I'm going to dive into the deep end, and we're going to look at using silicon photonics chip. We're using the silicon photonics chip as the integration platform, and then we're going to go to optical engines. These are TSV-based integration with analog electronics. And then we'll talk about integration of optical engine with a switch ASIC. So 2D, 2.5D, 3D. We're not going to have a fight today. I'm just going to claim it's 2.5D and explain to you why, and then we'll move on. All right? Okay. To build a 2D platform on a silicon photonics chip, you need to be able to integrate a number of components, the analog components on it, TIAs, drivers. In this particular case, we even integrated a V-groove fiber-coupled structure on it. And we had some space, so we threw in single-layer capacitors, lasers, and muxes and demuxes. This was a two-channel prototype that we were building. The reason why I call it just 2D because a lot of this was wire bonded out onto a substrate. It wasn't actually communicating with the substrate through a TSV of any sort. Sort of starting to get a feel for this level of integration. So we've actually stacked the electronics individually on the silicon photonics, using silicon photonics as the layer. The thing about this is nothing is really that simple. A simple optical engine assembly, perhaps. The assembly is simple. So dual channel optical engine assembly, we just put it on a PCB, external RF connectors. This is several years ago when we started working on this thing. To actually get it to the next level, we had to do a few things. To up-level this integration. But before that, integration of DFBs, there's always a question of whether you do it the way Intel has, which is great. You put an indium phosphide active region and co-process. We chose the other approach. We stuck a processed laser diode directly on the silicon photonics platform. That gave us an option to have a known good die. And of course, you have to figure out how to align it vertically. Where do you stop? Where do you align it right and left? With modern alignment machine these days, you can pretty much do a lot of these things. And the lasers are stable. And that is actually the pure spectrum of a DFB laser, by the way. It's not like it's oscillating or anything. We looked at it biased from 2 milliamps to 80 milliamps, 16 milliamps to 80 milliamps and 2 milliamp steps. There's no reflections. So you can actually stick these things onto a silicon photonics platform. And they're stable, and they work, and you can actually build finished DFB lasers. And never look anything under SEM. They always look ugly. So the next stage is, can we get to the point where we actually have drivers TIAs? DFBs on a silicon photonics interposer, by the way, which have TSVs. And this is what we started working on next. And you can have TIAs and drivers on a silicon photonics interposer with vias and bumps, and then you go right through this multi-layer organic substrate, and then voila. So you actually have a true, it's almost a 3D integration. We call it 2.5D because I have a 2D on a substrate. It's not a HBM, so I don't want the HBM people to kill me. So it's a TSV-based 2.5D integration of silicon photonics interposer and high-speed substrate. And you can design the whole system to be optimized. This is a very interesting design exercise. And then you build it in this case, on an 8-inch wafer. The module is fairly small. And then out of the 8-inch wafer, you get a little silicon photonics engine. You stick it on a substrate with DSP chips on it, microprocessors, decoupling cabs, which you need lots of them. But I'm not taking sides here. This light engine design could be used for pluggable modules as well, by the way. It doesn't have to be a CPO or a near package optics or an optical module. It's all different forms of an optical module, whether it's pluggable or not. It seems to be a religious discussion, but it doesn't have to be. It could go one way or the other. And then what you do with these things, this particular module was designed to operate both at 200 gigahertz, 200 gigabit per second, and a 400 gigabit per second FR4 mode. That's one of the nice things about this optical engine. It wasn't just optimized for one speed. You can actually be backward compatible. And since it has a lot of excess bandwidth to operate a 400 gig mode, the TDAQ for the 200 gig mode was was pleasantly surprised how low it was. And the 400 gig mode, we came in at a TDAQ of about 2. And overall, it's a good module and performs as it's designed and made. What we ended up doing with this one particular application, Teralink 7 or TL7 is a switch that Marvell produces. We built it on a substrate, on a PC board actually, not quite a substrate, on which you had all these light engines that I showed you in the 2 slides ago, together with the Teralink 7 switch. It's a fairly large board, but this was more of a proof of concept than anything else. And we ran live traffic, not here. This particular display was at OFC this year. What you do is you have an external traffic generator and then do what most people do. You connect it to one port, snake it through the switch, and it comes out the other end. And Chimera, by the way, is the GUI name, kind of goofy, but nothing else. But it was running live traffic, and we stuck 5 kilometers of fiber in there to show that, it passes FR4 traffic. And that's the integration of switch and optics. These things are possible. You can go to the Celestica booth, and this particular sample is on display. We're not running live traffic. And you can actually get to fairly complicated optical assemblies with electronics and build these things. A lot of it's for speed, but we've removed some number of SerDes interfaces, and there's a lot of power savings as well. And I was told needed to have a call to action slide. Didn't know what to put in there. And this is a technology demo more so than anything else for heterogeneous integration. A fully integrated switch and optics box, as again, Celestica booth, and you have more information at these websites that you or this pages on Marvell that you can look at this. Thank you. No time for questions. No. All right, Frank, go for it.
Okay, Radha. So you talk about integrations, right? So
yes.
Currently for the EMLs, everything, right? They already for DSP already integrated with drivers.
Yes.
So for the currently, right? For the SiPho, do you have a plan for that? But even the driver TIA probably will be from the DSP chip.
So that's a very good question. The silicon photonics today. Today's DSPs that Marvell sells have an integrated driver for silicon photonics. We've already crossed that. And the TIA is an interesting question. At a lower data rates, it's a question of building high performance TIAs in the silicon CMOS node. That's the challenge. CMOS stages, for those of you who work on circuit design here, they don't have a whole lot of gain, and by the time you stack up enough stages for gain, you're running into a parasitic problem. So it's a well-known problem. For some of the AOC applications, we actually have DSPs with TIAs and drivers. You're absolutely right. We're going in that direction. And at that point, the integration will look a little different. That's why I labeled the stock 2.5D integration, because the application it's more of an application space and how you would do it as opposed to this fits this particular product. Okay. Okay, good. It's a friendly crowd, so I better quit while I'm still ahead. All right, thank you.